Hello, Science Fam. We are overlapping now with physical phase changes, but also going to be looking into the energy it takes to actually go from solid to liquid or liquid to boiling off as a gas. And to do that, we're going to learn a few new vocabulary terms, things like heat of fusion, heat of vaporization, and from there we can do actually some pretty straightforward, simple algebra and math to determine how much energy is either put into the system or taken away in order to go, again, from something like melting solid to liquid or freezing from liquid to solid. So let's begin. Just a quick recap, we did go over endo and exothermic. Remember, if the system is gaining heat, it's endothermic. And don't forget, that means that Q is a positive number. The heat or energy is positive because it's gaining heat. Exothermic is the exact opposite. It's negative because it's losing heat. So as we go up in energy, we know that that has to be endothermic because you're gaining energy. And if you're going to go from a gas to a liquid or a liquid to a solid, you are losing energy in order to cool it down, in order to freeze or something like that. So that would be, again, exothermic. This is all the vocab that you're expected to know, but again, if you don't know, you are expected to know what melting and boiling is. Remember, melting is going from solid to liquid, and liquid to gas is boiling, and then vice versa. If you're going from gas to liquid water, that's called condensing, and liquid to solid is called freezing. Remember which is endo and which is exothermic. So in order to determine how much energy is actually being used, taken in, or given off, it does take a certain amount of energy to melt or freeze a substance. So if we're ever trying to figure that out, if we are trying to figure out what it takes to melt something, we would need a term called the heat of fusion. And that's just how much energy is absorbed by that specific substance when it's melting. Remember, melting is going from solid to liquid. And we know for water, right, that happens at 0 degrees Celsius. Now, the heat of fusion is specific to whatever object you're talking about. So in this case, since we're talking about water for the heat of fusion, it takes about 334 joules for every gram of water. Now, why would we even need to know that number? Because we could plug that into this simple equation, that heat of fusion, which is 334, times it by whatever mass you have of water, and that would give you the total amount of energy that it took to actually melt that water, or I should say that solid ice going into water. All right, so we're going to use this equation in a little bit, and it's really straightforward. It's just a number times the mass of whatever that object is. And again, don't forget, this is specific to water, but if it was a different substance like iron or copper, the heat of fusion would be a different number. To go opposite, instead of melting something, going from solid to liquid, what if we wanted to freeze something and go liquid to solid? If we did liquid to solid, you would need what's called the heat of solidification. And really what that is the amount of heat an object needs to lose. Notice there's a negative sign here for the number. How much energy you need to lose in order to solidify it, to go from that liquid to solid. So now that this is talking about either going from solid to liquid or liquid to solid, what about the phase change for water that we know about when we're going to boil something? Or if it's a vapor and we're going to cool it down and condense it back to a liquid. So let's look into that right now. So right here we have the heat of vaporization versus the heat of condensation. Heat of vaporization is not a clever name. It's when we're going to put in heat, so that's an endothermic reaction or process, and when the heat is absorbed, we're going to actually make the water boil. So that means we're going from a liquid to a gas phase. Now we know that the liquid to gas phase happens at 100 degrees Celsius for water. So if it's before 100 degrees Celsius, we know that water is a liquid. Once it's at 100 degrees Celsius, we know that either liquid or gas is present. But when you're going from liquid to gas, in order to figure out how much heat is necessary, how much energy, we use the heat of vaporization. Now, the heat of vaporization for water is a positive 2,260 joules per gram. Now, the reason the units, again, are joules per gram is because when you multiply joules per gram times mass, which is grams, grams is going to cancel out, and you're going to be left with your units of joules, which is the unit we need to figure out heat or energy. So the heat of vaporization can help us figure out exactly how much energy was used in order to convert that liquid water into gas. Okay? So the heat of vaporization, that HVAP, excuse me, is important to know that value so that we can figure out the amount of energy. Now, opposite of that is the heat of condensation. Remember, when water condenses, it really goes from gas back down to a liquid. And don't forget, that still happens at 100 degrees Celsius for water as well. So if an object is above 100 degrees, like 101 degrees Celsius, that water is still in the gas vapor water phase. All right, but as soon as you get to 100 degrees, you could have both gas and liquid water existing at the same time. Now, once you hit 99 degrees Celsius again, remember that's cold enough for water to be back as just a liquid. So remember, during those phase changes, the temperature stays constant, and the phase change between gas and liquid, from between water and steam, is really 100 degrees. That's the temperature. Now, if you're condensing, that heat of condensation has a value too. And that value is exactly the same as the heat of vaporization, but it's negative. It's negative 2,260 joules per gram. The negative, remember, means that you just lost that heat. So if you're losing heat, we're giving it off, the system is giving it off, that's an exothermic reaction. Where again, the heat of vaporization, since you're putting heat into it, that's an endothermic reaction. But again, to use this simple equation, the energy is going to be equal to this number, the heat of condensation, times the mass of the water. And when you do that, that will give you your Q value, or your heat or energy value. Okay, so let's use these values to help us figure out, all right, hey, say I have a block of ice, and then I melt it, and then I heat up that liquid water enough to boil it. How much energy does that take to do all of that, to turn that ice into gas, or to just simply start melting an ice cube? We can use two equations. We can use our equation Q equals mc delta T, the change in temperature, and we can also use these equations where we use the either heat of fusion, heat of vaporization, whatever, times the mass. When we put all that together and add up those changes in energy, we can figure out the total energy used in the system. Let's try a couple examples of that. All right, so if you look at this chart up above here, the question is, how are we going to calculate energy changes of water? Well, first of all, if you look, this is broken into 4 sections. This is where you would have solid ice, okay? So let's think of just water. And the ice would slowly be warming up. Now, when you warm up ice, we think of ice immediately melting, but that's not what we're saying here, right? We know that when ice starts to melt, that's at 0 degrees Celsius. So we've got 0 degrees Celsius at the beginning and end of this B part where it says melting the ice. So that means if we're warming the ice over here, this is in the negative degrees Celsius. Could be negative 20, working its way up to negative 10, working its way up to 0 degrees Celsius. But this section means that solid ice is below 0. Now, we know that once we melt ice, that solid to liquid transition is at a constant temperature. Hence, why the energy here, or the temperature, is at 0 degrees Celsius. But take a look at these two different boxes for this phase change. If we want to know the solid ice heating up to eventually get to 0, since that temperature is going to change, notice we use our mc delta T equation down here. But once we get to a phase change, we're going to use that equation that we just learned about in previous slides. And since we're melting, that's fusion. We would use the heat of fusion times the mass. Okay? Now, say you heat up that ice and you melt it enough that it's all liquid water now. Now, once that happens, liquid water starts at 0 degrees Celsius and would work its way up to, at the most, 100 degrees Celsius, because we know once it hits 100 degrees, it would start boiling. But because your liquid water would be heating up and temperature could be changing from one temperature to another, could be 0 to 20 degrees and you stop heating it at 20 degrees Celsius, could be 0 to 90. We have to use our MC delta T equation again because there's a change in temperature. But we've already used that equation before, so that should be no big deal. Now, if we go to boiling water, we know that liquid water is now at 100 degrees Celsius, and if you start boiling, it's going to turn to a gas. But remember, that phase change doesn't change temperature. So that boiling water process would be at 100 degrees Celsius. There'd be no change in the boiling water. But since you are boiling it, it would be using the heat of vaporization number that we learned about on the previous page. All right? So if we break this down again, now that we went through that whole chart, if you're warming ice, which is section A, that's this section right here, we would use the formula Q equals MC delta T. And because it's solid ice, we would be using the specific heat of ice, okay, which has its own value, and we can look that up. Now, if you're in part B where you start melting the ice, remember that's going from a solid to a liquid. That's a phase change. Because there's no change in temperature, it's just 0 to 0 degrees Celsius, we would use our equation Q, that's the temperature, that's the heat or energy, and we would multiply the heat of fusion, which is the number we use when we're dealing with the energy it takes to melt something, times its mass, and that would give us our total energy. Now, if you want to figure out the total energy it takes to take this solid block of ice, heat it up, and melt it into a liquid, because you're using sections A and B, you would use both of the separate equations, A and B, and then you would add those up for the total amount of energy. So once you solved for Q of part A and Q of part B, you would add up Q of A plus Q of B, and that would give you your total energy. And again, we're going to go through examples of that, but we're just starting to break into what's going on here. But let's look at C and B as well to kind of get an idea overview before we jump into specific problems. All right, so when you're calculating energy, if you are warming water, and again, that's liquid water, and its temperature is going up between 0 degrees Celsius and 100 degrees Celsius, in order to figure out that energy, you would have to use Q equals MC delta T. But since we're dealing with liquid water, you'd have to use the C value specific to liquid water, not ice. So that value for C in part A is different than the value of the specific heat, or C, for part C. So keep that in mind. So when you're doing these problems, you do have to know what phase your object is in. We're going to be doing these just for water since we did the lab where we heated up the ice cubes and turned it into eventually boiling water. So we'll focus on that. But you could do this with any element, a metal or whatever. You just need the specific values for specific heat, heat of vaporization, etc. All right? So say you get to 100 degrees, now your water is a nice hot liquid, and that liquid is going to start boiling, so we're going to convert it to gas. We know that happens because it's a phase change. The temperature stays constant. You're now in the boiling water phase. Because of that, whenever we're boiling something, we're concerned with the heat of vaporization number, and that's a number specific to each different compound or element. So for water, the heat of vaporization has a specific number, and you would multiply that by the mass of the water that you have, and that would eventually get you your energy or Q value. Now, say you had liquid water and you wanted to figure out how much energy it took to heat it up and to boil it all at 100 degrees. We would take our Q value for part C after you solve for it, and for part D, all right, so Q of C, and add it to Q of D, and that would end up giving us our total energy, or our total Q value, which would be in joules. So we're going to use this chart. Maybe we'll start at melting ice and then work our way to warming it up and boiling it. If that's the case, you would use B, C, and D. Maybe a problem, you're going to start as solid ice, and you're going to heat it up so it melts and eventually heat it up to, I don't know, like 30 degrees Celsius. Because of that, you would use A, B, and C equations and add them all up in order to get your total